Hey, how's it going, everyone? Welcome to the next topic, which is looking at networks and graphs. We had a quick look at networks the other day in our group activity, so we'll get started on the actual definition. So, a network is a collection of objects connected to each other in some specific way. So, for example, a telephone system is connected by different telephones, which is connected via satellites. And so we can draw that. So we've got our telephone, dodgy drawing. Okay, and it connects to the nice big satellite, and then that connects to the other telephone, so you're able to talk to each other. So that's an example of a network. So I can actually draw that, and we'll have a look at this shortly, as a communication network between objects. So these are our objects, and this is the communication, and we'll have a look at the specific definition. So network is a collection of objects connected to each other in some specific way. So consider the network represented in the diagram. So this is the simplest possible network, and we can label this as two different parts. So our our objects, in this case, number 1 and 2, is what we call vertices. And so that's the other vertice or vertex. And the communication between them, or the connection, is called an edge. So a few different definitions here, and we're going to eventually create a glossary of lots of different definitions. So I got a famous problem, the Königsberg Bridge problem. So the problem asks, is it possible to make a tour of the town of Königsberg, starting and finishing in the same place and crossing each bridge just once? This is a famous problem, and this is the foundation of graph theory. So essentially we can draw or recreate this situation. So you've got different islands and bridges connecting between them, and we can make it as a simple diagram. So, for example, this island here would be one object. The island over here is one object because I can connect all three bridges. I'm basically on the same path. I don't need to cross any bridge to get to any of the others. And same thing over here and here. So on the side, I can actually redraw this as there's my first vertex up the top, the second vertex in the middle, one down the bottom, and one on the side. So there's my objects for vertices. Now the bridges, I just need to connect. So this first vertex connects twice to the middle vertex. So I can draw two lines there indicating two bridges. It also connects to the one on the end. And down the bottom, this one connects to the one on the end. And it connects twice to the one in the middle as well. So there's a network. So I've redrawn the situation in the real world to something more simple, indicating vertices and edges. So pause the video now and have a go. Draw out this network and see if you can find a pathway in which you start at the same place and you cross each bridge just once. So I'll give it a quick little example. So I might start at this vertex here. I'm going to go along this bridge to this vertex here. From here I can only go back this way to this one here. And then I'll go across this bridge here, and then I can go across this bridge here back to my original position. The problem is I haven't used this bridge and I haven't used this bridge. So in this situation, that's not what the question's asking. So I need to figure out a way in which I can start at one vertex, go around every bridge just once, and end up at the same place. So see if you can figure it out. So pause the video and have a go. We'll talk about that network, the bridge problem in class. So if you find a solution, make sure you jot it down and we'll have a look at in class. So stay tuned for the answer. Degrees of vertices, or the degree of a vertex. We had a look at this in matrices. So each vertex may have a number of edges connecting to it with the rest of the network. And this number is called the degree. To determine the degree of a vertex, we simply count its edges. So, quick little example, if you go back to our bridge problem, this vertex here has 1, 2, 3 bridges connected to it. So its degree is equal to 3. So it's got 3 bridges connecting to it, or 3 edges. So that's what we're talking about with degrees. And we'll do an example shortly. If 2 or more edges connect the same pair of vertices, they are called parallel edges or multiple edges, and all of them count towards a degree. So what that's saying is, we'll use white. So we've got one vertex, another vertex, and it's connected as parallel edges. So it's connecting basically one vertex to another, and we've got 2 different pathways we can take. So these are called parallel edges. They run parallel to each other, and both of them count towards the degree. So the degree on this side would be equal to 2, as was this side over here. But if we had a third vertex and connected it like so, this degree here would be equal to 3. So even though we've got 2 edges from the same vertex connecting to another vertex, both of those count as their degree. This situation over here, where we've got one vertex connecting only one way to another, is called a simple or a single connection, because there's only one way. It's very simple. So we'll have a look at works example 1. So count the number of vertices and edges in the network shown. So first thing, probably want to label our vertices. So I'm going to 1, 2, 3, 4, and 5. Might be towns, could be telephone situation as I indicated before, or it might be another bridge problem. So we want to count the vertices and edges in the network shown. So for number 1, we've got 1, 2 edges connecting to it. So at 1, our degree, if we were looking at the degree, would be equal to 2. So vertex 1 degree would be equal to 2. At 2, we'll have 1, 2, 3. At 3, we'd have 2. At 4, we'd have 1, 2, 3, and 4. And at 5, we've only got 1. So even though it doesn't specifically say the degrees, I'm just expanding on what we were just talking about. So it does ask to count the number of vertices and edges. So we've got 1, 2, 3, 4, 5. 5 vertices, and we've got 1, 2, 3, 4, 5, and 6 edges. So that's all we need to do for that one. Just giving a bit of a background into networks and graph. So the second one, so this is actually specifically talking about the degree of each. So again, have a go yourself. So pause the video and work out the degree of each vertex. So vertex 1 would have 2. Vertex 2 would have, well, that counts as one edge, even though it's a loop. So it connects one to the other. So that would be 1, and you've got 2, 3, and 4. At 3, the degree is 0 because we have no connection between any other vertex. 4, we've got 1, 2, 3, 4, 5. And at vertex 5, we'll have 1, 2, 3, 4. Okay. Worked example 3. So we've got label the edges, the vertices and edges for the figure shown. So the vertices I'll label as capital V, and the vertices inside the network is 1, 2, 3, 4, and 5. So just listing all the names of the vertices. Okay. So first label the vertices, then we examine each edge in turn. So at vertex 1, which connects to vertex 4. So vertex 1 connecting to vertex 4. Is looking at this edge over here. Vertex 1 to vertex 2, well, that's talking about this edge here. And then vertex 2 and vertex 2, that loop connects 2 to 2. So we label it as 2, 2. And we can do the same kind of pattern for all of them. So vertex 2 to 4, and we've got 2 to 5, 4 to 5. Now, there's 3 parallel edges. So we literally just write it out as 4 to 5. We've also got 4 to 5 and 4 to 5. So we just write it out 3 times. That's there indicating each edge. And vertex 3 has no edge to it. So in total, we should have so 1, 2, 3, 4, 5, 6, 7, 8. 1, 2, 3, 4, 5, 6, 7, 8. And so, as I said before, labeling the vertices is that first part there. So it's just labeling in those squiggly brackets 1, 2, 3, 4, and 5. And my edges would be capital E, and then I'd put 1, 4, 1, 2, etc. Work example 4. So construct a graph from the following list of vertices and edges. We've got vertices as A, B, C, and D, and E. So we've got A, B, C, D, and E. And the edges, well, there's an edge between A and B. So So just connecting the edges, A to B, or, yep, A to C, there's one down here, A to D, B to C, B to D, B to D, again, meaning that's parallel, C to E, D to E, and E to E, meaning there's a loop. Alright, not very neat diagram, but you can do a nice one in your book. So that's his work example 4. So it's just constructing the graph or network. And last one, represent the network shown as a matrix. So we've had a look at this before in chapter 8. So if we remember how to do that, so we've got a nice big vertex matrix, sorry, and we've got A, B, C, D, and E across the top and down the side. Now, considering vertex A, well, it connects to B, D, and C. So vertex A, we can put a 1 in B, C, and D. Moving on to vertex B, there's 1 between A, there's 1 between B to C, there's 2 between B to D, and there's no vertex to E, edge to E, sorry. So vertex C, there's 1 to A, and there's 1 to B, there's 1 to E, and that's it. Vertex D, there's 1 that goes to A, there's 2 that goes to B, and there's 1 that goes to E. So the rest, actually we'll have a look at E as well. So E to C, there's 1 E to D, and there's 1 that actually goes from E to E by itself. So the rest is just filling in the gaps, which are all zeros. So there's a vertex or a matrix for the network shown. And if you remember, this is actually our one-step matrix because we're just looking at going from one vertex to another. So that's 9.2. Have a go at the questions. Stay tuned for the next video. Thanks.